All right, Paul. So it turns out that when the particle physicists look at the Higgs theory, the Higgs field, they predict that it's going to have this shape, the shape of a Mexican hat. And how can that help us understand the universe?
Well, it's a very good analogy to cooling water down. When the universe is very, very small, say 10 to the minus 50 of a second after the Big Bang, the energy level might be really very high up here. And that means the Higgs field is going to change in value anywhere from there to there.
Yep.
And on average, it's going to be in the middle. So it might be from quantum mechanical fluctuations briefly this way or briefly that way, but most of the time it's going to be zero. And because it's zero, that means the forces are all going to behave the same. So everything's unified.
So that means that at that point, electromagnetism, gravity, potentially, the strong force, the weak force, all going to behave the same because it's really the average of all of them at the same time.
Yes.
Because things are able to move throughout this energy diagram, which we have to think is not just being a single plane, but actually in multi-dimensions.
Indeed. Yeah. But of course, as space expands, it gets cooler. The energy levels drop, and they drop, and they drop, and they drop, until sometime, maybe about 10 to the minus 40 of a second after the Big Bang, they touch down here.
So you suddenly find yourself abruptly grounded, so to speak.
Yes, and then the energy levels will keep dropping, and now the field has to make up its mind. It has to go one way or the other. And so it's going to end up maybe over here, or in some other multi-dimensional Mexican hat in some other direction, but it's not going to be zero anymore.
So essentially it's going to plop down and then kind of slide down the slope one direction or the other.
And if it goes over here, it'll have to make up its mind. It might decide we're going to have a strong force that's strong,
Yep,
and a electromagnetic force that's weak, and a weak force that's even weaker. Or it might go down here and the forces might be permuted. So what we call the weak force in the universe over here might be a strong force, or some different combination of the laws of physics and the forces swapped around.
Right.
So it's got to make up its mind and give an asymmetrical outcome.
Right.
But how does this help us? Well, if that was all there was to it, it's a nice way to reconcile unification with symmetry. But the thing that's potentially very exciting for cosmology is, what if something gets stuck up here?
So this is the moral equivalent, that I'm coming down fast, jumping out of a helicopter, we'll say, with the parachute on, with a pair of skis. I'm going to go sort of heliskiing out of an airplane rather than a helicopter. And I land on a very flat plateau on the top of the hill, expecting to ride down the valley, but there's essentially no slope, so there's no place for me. I just get stuck where I'm at.
Yes, you can imagine it's almost like the universe being a ball. It's sitting on the top here. As long as it remains on the top, if the top of the sat is very flat, it won't go anywhere. Right. Eventually some random quantum mechanical fluctuation will start it rolling down one side or rolling down the other side, and which side it goes is going to be random. But in principle, if the top of the sat is very flat, it could sit up here for quite a long time.
So I'm going to be stuck at this very high energy level while the universe expands.
Yes, so the overall energy level of the universe will keep on dropping. It might get down to here, right, but all the time you're stuck up there.
Okay.
And that's what's called a false vacuum.
Right, so the real vacuum's down here at zero, and this top hill where you get stuck in, false vacuum.
Yes, and this false vacuum has energy relative to the true vacuum, which is the difference from there to there. And that is absolutely, absolutely enormous. 1 cubic millimetre of the universe back then, the amount of energy in the false vacuum then would be equivalent to taking absolutely every galaxy we can see in the observable universe and combining it with an antimatter galaxy the same amount, destroying the entire universe, converting it to raw energy, and that would be just 1 millimetre of the universe back then. In fact, it's a million times less than 1 millimetre right then. Right. So absolutely staggering amounts of energy, and hence mass, because they're interchangeable, in every tiny bit of space that's stuck in the false vacuum.
Okay, so if we think about how this is going to look in one of our equations, the Friedmann equation that we talked about, it's going to be interesting because we have the change of the scale factor, and we're going to have this amazing amount of energy in the form of what we call density, but remember energy and density are interchangeable, so that's going to be huge. So you're going to have a constant times a huge value is what the the change in the size of the universe is going to be proportional to.
Yes, and so if you take the square root, you're going to get a dot over a equals square root of something enormous, which is still pretty enormous. Bring a over this side, you're going to get a dot. The rate of change of a is going to be proportional to an enormous amount times a. So what that means is the universe is going to be expanding really fast.
Right.
And that means it's going to get bigger, and then it'll expand even faster.
So it says that the rate that the universe expands is proportional to how big the universe is. So if I have my size is 10 and I'm changing by 10% per second, then that would make me 11, and then my next change would be 10% of 11, which is 1.1, and that's what we call exponential growth, like inflation, for example, of an economy.
Breeding of rabbits in Australia.
Exactly, breeding of rabbits. Anything exponential has that characteristic. So we expect exponential growth.
So it'll look something like this. Here's the scale factor of the universe versus time, and it will grow, and as it grows, the scale factor gets larger, so it grows faster. So the scale factor gets even faster and faster, and up like a rocket. Actually, much faster than a rocket.
Yes. I wished I had a rocket that could exponentially take off. But all right, so we're going to have an interesting universe that is going to grow incredibly fast.
Yes, and this is the core idea of cosmic inflation.